Before we actually start this experiment, I want to go over some of the experimental setup and the way we're going to collect the data and analyze it. On the right-hand side here, we see the experimental setup. We've got a digital balance to two places that we're going to use for measuring the mass of our solutions. One of the assumptions that we're going to make in this experiment is that the density of all the solutions is equal to 1, and that will allow us to use mass as a substitute for volume, because we'll be able to measure the mass, convert that into volume using the density. In the upper left-hand corner, we have a conductivity sensor. So the conductivity of a solution can be used to measure the salinity or the content of ionic compounds in a liquid solution. I've got some table salts and a variety of glassware, in a sense. I've used a straw that I'm going to use as a straw for pipetting solution into my sample, and it works pretty well. I'll do another video perhaps showing that that this is a reasonably good technique for an at-home lab. Okay, over on the left-hand side, we've got a template of an Excel spreadsheet for the data collection. We've got 3 different sections: the experimental setup data, the data collection, and then the data analysis section. In the experimental setup and the data collection, you'll notice that there are some orange colored boxes. Those are data that we actually have to put in. The ones with the gray and orange are data that will be calculated for us. This one here is fixed, so the desired salt concentration is going to be fixed at 25 milligrams per milliliter for this experiment. And then these in the bottom left-hand corner are our outputs. Okay, a couple things that we do need to know before we get started are some masses. So I need to know the mass of the centrifuge tube, so I'm going to put that on there. And the mass of that centrifuge tube is 12.13. And I need to know the mass of the container that I'm going to use for my to hold my sample. And so that goes down here in the sample cup, and that's 14.62. Great. Now I'll go get some tap water, and we'll get going. Okay, I have some tap water in my sample cup, and if we measure that, that comes to 359.55. Put that in there. And we'll weigh the water that's in my centrifuge tube here, 48.99. Okay, and I will put a cap on that one so that it doesn't get spilled or knocked over. Okay, so we those two measurements, the measurements of the centrifuge tube and the sample cup weights, those aren't going to change. The water in the tube, this tube here, is actually going to be used to hold the standard, and then obviously my sample is in the sample cup. And if we take a look at what we've done here, the mass of the water and volume of the water, obviously those are the same value because the density, remember we're assuming the density is 1, so that's the same numerical value. So we've got 36.86 milliliters of water, and if we want to make that water a total concentration of 25 milligrams per milliliter of salt, this tells me I need to add 0.92 grams. So let's go ahead here and measure out about 0.92 grams. We're a little bit high. I'm going to actually leave it at that. Okay, so I'll put the actual value, which is 1.06, and it does calculate the actual concentration is around 29 milligrams per milliliter, and we'll take that, put that into here. Fair amount of shaking. If we take a look, it may be a little hard to see through a cloudy plastic, but I can see that this salt is a little bit cloudy. If I take a look at the ingredients, this is normal table salt. One of the additional ingredients in commercial table salt is calcium silicate. Calcium silicate is an anti-caking agent that is used to prevent clumping of your salt. But it is not soluble in water, so the cloudiness is due to that. So that's going to be a source of error for us. The actual salt concentration is going to be less because what we just measured was the weight of table salt sodium chloride plus a little bit of calcium silicate. So we may need to take that into consideration, but probably not, because when I did some digging, um, the amount of anti-caking agent used in Morton salts is about 0.2 to 0.7% by weight. That's below the precision of this experiment, so we'll probably be okay for that. Let's go ahead and now weigh. I do need to weigh this without the cap, because I know the weight of the bottle without the cap. And there we are. And so the salt water in the tube, 49.99. I do this just to make sure that the, 49.98. Just to make sure that we didn't lose any. If I measured 1 gram and I knew that there was 48.99, so this number here plus this number here should be the same as row 9. Notice how the sum, it's down here in the bottom, is 50.05, whereas I'm reading 49.98. So there is a little bit of liquid that was lost in the, or either liquid or salt that was lost in the transfer. It's possible that that liquid is actually just, oh, there we go, is just that little bit of liquid that's in the cap. So we're not going to worry about that, but just another potential source of error. Okay, so now we can go ahead and start our measurements. Again, 359.55. Okay, so that looks good. So what we're going to do, since we can't measure volume precisely, but what we can do is measure mass precisely, I'm going to measure the mass both before and after I do make a conductivity measurement. And from that information, I'll be able to determine two things. One, the volume of liquid that I actually added, and if I lost a lot of liquid during the analysis. So mass before and after should be pretty close to one another, and then the mass after and the mass before, the difference between these two should tell me the volume that I actually added. Okay, so let's go ahead and get started here. I'm going to oops. If I'm going to get started, mass before, nope, this is 0. So, oh, got to pay attention here. So before, the very first experiment is measuring conductivity before we've done any additions. So the mass before is 359.54. And then let's go ahead and make a measurement here. I read 477, 478, 477. We'll do 477. And the mass after is 359.36. So yeah, you see that we lose a wee little bit of liquid. I'll slow down to keep the cap on just to play it safe. The mass before, go ahead and measure the mass before. And let's measure the conductivity. Let's call that 836. And 360.89. Wash, rinse, repeat. Call that 1266. We'll call that, yep, 1266. Got a few more here to go. I keep stirring until I see that the conductivity is bouncing back and forth between two numbers or so, as opposed to drifting downwards. And I see 1651 seems to be pretty stable. And measure that. If you notice the way we've done this, the way this template is set up, it's already telling us in the lower left-hand corner what what it thinks the concentration is. Part of the exercise here is for you to figure out what the various calculations are. I'm not going to show you the calculations because we've done so in previous videos. Let's call that 2003. Of course, if you give it a shot and you've tried to do the calculations and you can't figure out what they actually are, we can certainly talk about it. But the point is, I want you to give that a shot before actually giving up. Okay, so that was our last addition. Let's make sure we've collected all the data that we're supposed to. And get the conductivity. .28. Not 23.28, 23.28. And there we go. We've got a very nice linear standard addition curve over several milliliters. I don't have the R squared of the best fit here, but that's probably it looks very nice. At the end of the day, the method of standard addition tells us that the initial concentration or the salinity of of the tap water here is 0.188. We probably only know this to 2 sig figs because of all the other measurements. So let me do something like that. 0.19 milligrams per milliliter, and that is pretty close to it's within the limits that one would expect for tap water in New York. 0.2 milligrams per milliliter or 200 milligrams per liter is the standard. So that number seems reasonable, and I'm pretty happy with that result. So next up, there are several steps that you need to do. The first thing is you need to create this template based on the results that you see here, because we're going to do this experiment 2 more times. One, we're going to try some filtered tap water, also from my house. So the only thing that's changed is that instead of going straight from the tap, it's going through a filter first. And then we're going to compare these results to distilled water that I snuck out of the lab before the pandemic, and we will see where we go. I will not put the Excel sheet up for those. I will only show the data collection. Your job is to collect the data that you're supposed to and put them into your template. So the water I have here is the filtered water, filtered tap water from my house, and I'm going to go through this experiment without doing a lot of chatting. Your job is to monitor, collect the data, and generate the results, similar to what we did with the first trial. I'm not going to say a lot. If I do make mistakes, then keep those in mind in terms of experimental error. This is a raw and uncut video. I'm not going to go and fix mistakes. This should be our last one. Okay, that completes the data collection for the filtered tap water. We do have one more trial to do, and we're going to analyze a sample of distilled water as a control experiment. And for our last part of this experiment, we're going to be looking at distilled water. So this is my sample of distilled water. Again, I'm not going to talk too much during the experiment. Go through and collect the data, record the data that you think you need in order to analyze this, similar to the way we did first trial. As with the filtered tap water, I'm using the same standard as we created in trial number 1. So the actual salt concentration of the standard is something that we've already calculated. And this should be our last one. And there we go. So we have complete sets of data for tap water that's been filtered, and distilled water. I went through the data analysis and collection for the first trial, and it is your responsibility to crunch the numbers for the second two trials.